The broadcast is now starting. All attendees are in listen-only mode.
Hello everyone, and welcome to this webinar. First, let me introduce myself. My name is Vladimír Příbramský. I'm a product manager responsible for modeling, analysis, and engineering report, among other things. And today I prepared for you, with my colleague Dominique Vipers, presentation and webinar regarding modeling and analysis of steel tanks and other cylindrical shells. So in this webinar, we are going to use GoToWebinar application. For the time of the webinar, you are all to be muted, and so you can't ask your questions verbally. But I encourage you to ask your questions or place your remarks in the questions box in the GoToWebinar applications, and also to notify you that this meeting is being recorded and it will be available for you or for anyone else willing to see it in a few days time on YouTube channel of SCIA company. So let's go to the content of this webinar. We have a lot to cover. First, I will speak and show you something about modeling of rotational shells. There are stiffeners, either by 1D or 2D members, and using cutouts between 2D shell members. How to apply loading by either filling or wind, which are very specific for the rotational shells or steel tanks, silos. Then we will speak about analysis, how coarse or fine define the mesh, how to use local mesh refinement and for linear analysis. I will show you a steel check made by one of my colleagues in design forms and show you where to find it. And I will just quickly cover the general plasticity. And at the end, briefly, I will talk about the engineering report, how to create structured document in engineering report, how to work with indented tables and images, and most importantly, how to use own templates for similar projects if they are set as well as possibly while creating them. So let's quickly go in pictures through the webinar content. We will show you how to model the steel tanks by shell rotational element, add some stiffeners and structural elements of supporting structure from beams, and also how to load it with filling or wind load based on the correct or as precise action as possible. To start with, I have some basic tips about modeling approach for stiffening members on such shells, and here I prepared just quick overview of 3 different approaches. The first approach is modeling stiffeners right by 2D members, by shells or plates that are intersecting the base shell of the rotational structure. The second one are 1D members that intersect with shell elements, and the third one is stiffening by 1D members that are only placed on the edges of the 2D members. Here there is very important note is that only the first and third option will work correctly, as you can see from the deformed structure. The second option, where you are, if you are using 1D members to act as a stiffeners to single shell element and not placing it on its edges, will lead to wrong results because the elements are not connected all the way through. So this is very important to keep in mind and to choose an approach that suits you the best, but is guaranteed to give you best results. What is specific in terms of wind load on cylindrical shells? This in this way we speak about Eurocode approach, is that it has both varying magnitude based on height of the structure and based on the angle of the uh, structural element compared to the angle of acting wind. These actions have big influence on the structure, and I will show you how to quickly get to results such as these. We will talk about local stability analysis of the steel tanks, how to calculate them, how to set up the mesh so to get appropriate, correct, as correct as possible results, and how to use these results to apply for a local stability check of basically coming from the stresses or principal stresses in the structure, and using our developed check, you can see where the structure is okay and where it fails. So let's dive straight into SCIA Engineer. I will show everything uh, from now on live in the program, and I start with such a simple drawing. I prepared here a structure section made by simple lines just to get modeling quickly. Here you can see that the silo is approximately 20 meters high with diameter of more than 3 meters. Let me delete or hide these dimensions by using only drawing from the tank, and we shall start with it just like that. So now, if I want to start adding shell members, I will keep in mind that that was also visible from the images. I have vertical stiffeners or stiffening members placed by 45-degree angle. So that's also how I will divide my structure with. So if I go to structure and select shells, I will be using the surface of revolution, and here I can have some simple settings of material, thickness, and layer, and I can now start inputting the edges of the tank. I am using snapping settings on, so I'm only snapping at the end nodes of any lines, just like that. What I can use now is either to select the lines with this, or I can very simply click in order to get the lines active. If I just quickly write on the first two, here I can write 45 degrees. Working plane is axis Z, and while hitting OK, I have to define the center of rotation. Conveniently enough, I put this in the center of coordinate system, and by hitting OK, I have the small shell available here. I can do this in a bunch for all the items that I have here. It will take only a little bit of time. Here I will use division of the members by the height, so I can then optimize the structure based on the level in the tank. So let me click only few more times. So all the lines that are to be rotated by 45 degrees are now selected. If I hit escape, I have the angle set 45 degrees. I define the center of rotation, and by hitting escape, you can see that the segment of the shells that I'm going to use for my silo is in place. Now what I can do is I can select all the elements I can place them in the layer that I've prepared for these elements, and I can of course select them all and work more with them. Now something that is very handy for making structure like this is using the multi-copy uh, multi-copy tool, and by the multi-copy it means also multi-copy with changing of rotation. So it's copying and rotating at the same time. So what I want to have is having 8 segments along the silo by 45 degrees. So I hit something like that with OK, and straightforward I have basically a whole silo modeled with the longitudinal stiffeners and different shell elements around it. What I want to do further is to show you how to work with cutouts, because sometimes you have an openings or crossing members in the silo, and here I can model this for example by swept surface function, which is working very similar way. So let me put it in the tank section. Here I prepared an circle for pipe leading into the silo. I can use the select line feature, select this circle, uh, apply with escape, and the surface is then defined by two points, just like that. If I show how it looks, there is rendered surface. Let me select this surface and these two members of the roofing, and I enable them by activity, uh, just only them. Now if I want to use the cutout function, I have to first find the intersecting line, and I can do this by using the connect members and nodes. But just by hitting OK, I can see that two intersections were generated, and I can see them right around these uh, shell entities. Now if I go to 2D member components, here I have the cutout. I can click it. I can select all members that are here, and by selecting parts that are not to be in the model, I can remove them. Now if I look at the rendering, I can see that the surfaces are being cut out from both sides, leading to a structure geometry in the way that I wanted it to have. Just quick other thing is I can add lid to the pipe by again using the select line feature, and here I go. I can do the same thing, of course, for this lid, hitting the select line. Then I can select, or I have to select all the eight curved lines on the top, and the 2D member that perfectly fits the structure underneath, or the topology of the structure underneath is created by this means. And of course I can do I could do the same in the on the bottom line, or the bottom surface, just clicking all these, and here I go. So this is for the silo itself. Now I can go on and start inputting the supporting members by means of 1D beams or 1D members. So let's start with the uh, supporting columns. Here I have the HEB profile to support the tank from here to this inner edge, and also I will place the same from this point to this point. I would like to have these beams rotated in order to have the HEB member modeled this way. Apply escape. I can also model, let's say in this case, I prepare it in a way that I have also some foundation blocks available together with fixed support in this case. And also let's model a few diagonals. Currently I'm modeling only one column. I will then use the same feature as before, and I will rotate everything along by the multi-copy. So let's get the snapping on points again, and I can create these beams in few seconds. Okay, these beams I shall provide with hinges, for example, just like that, and I can go further on by using by modeling the stiffening of the steel as in the pictures that I showed you. For that, I will use this profile to make a longitudinal or vertical stiffener from here to here. I will also rotate it by 90 degrees, and I will use the member system line as left in order to having it aligned with the outer surface of the silo. This member I want to have rotated because the rotation by the multi-copy, as I described before, is also rotating the cross-section, which I found here very convenient. So I will just use it in a way, and by very quick manner, I have the beam here as well. This one is secondary stiffener, so I can use, of course, different profile for this one. So now, if I select all the 1D members that I've inputted, so all those stiffening members and all of these bracing or the column members, I can use the multi-copy again. I want to have 4 copies. It includes the original ones. This time I want to rotate it by 90 degrees. By hitting OK, I'm basically done with the modeling. Let's have a look at the rendering, and you can see that all these members look very similar to what I showed you. Of course, they are in the same layer for now, but that is something that I can fix quite quickly. Let's place them under support layer, and then by selecting these members, putting it back to tank. So now I have 2 layers in my project. One is for the tank, and one are for the supporting members. So basically, at this point, the modeling of this example is finished. I want to connect nodes and edges in order to get internal nodes and internal edges on all members, and I can go and continue with the loading of or applying load on the silo tank. Here I have a report of what was connected to what, and if I hide the rendering, I can see that nodes were aligned or were attached to the members of columns. I can see that here I'm missing supports, so I can fix that easily as well, and that on these members I don't have hinges, so I can select them all by this multi-select feature, add hinges on both. Yes, I have few inputted already, so they can be inputted again, and here I can see that I have also attached shells to each other, and the members that are placing as vertical stiffening system here is connected automatically to the shells because they are acting on their edges. So let's go for loading. for loads, I have here few predefined load cases that I'm going to fill with content. So I have the load case for filling of the tank, some dead load, some imposed load on the roof, and of course the wind load. So let's start with those easy ones. Let's say that the dead load is represented by the weight of the insulation or any shielding of the tank. Let's put this like something like 0.2 kilonewtons per square meter. I want to act it on length and in global coordinate system. Now I can apply this to all these members. Not on the stiffeners, but on all other members, just like that. So the loading is now finished. If I want to have more on the roof, I can very quickly make a different value, of course. For the filling, I will use a feature of the free load, and I will create multiple. I will create two separate entities and work with it in a slightly different way. So first, I want the filling to act in the member local coordinate system, because every member of this load is acting as water pressure, in a very similar way. So it acts perpendicularly to the surface. If I select the member LCS and Z direction, which is the normal vector to the shell surface, then that is exactly what I want. Let me have a view from the front. And first, what I have to do when inputting free load, I have to select the coordinate system for inputting as I want to input it. So in this case, I want XZ coordinate system, because that's the plane that I'm working or looking at. I want to, in this case, I want not to have my filling all the way up. I want to have free 1 meter height from the top left for thin air. So I can, by snapping points, use here that I want to divide curves by 1 meter length. By hitting OK, I have now snapping points at the 1 meter height from the top. I will create two loads. First one with this shape, and second one with the conical, let's say conical shape like that. And let's say that of course I want to be in as a not uniform load but varying load, and I can say I can estimate the values to be, let's say, like this. In the area of the stiffening ring, it will be 116. That will be also this area, and at the bottom of the shell, it will look like that. So, so the distribution is linear in this case, or nearly linear, and I can now select items or members that are acting with this load. So, and that is what I want to actually do, because otherwise the free load will be generated even here on the stiffening ring. That is, but that's not the realistic behavior. So let me select both these members. I want to have the validity for all, but I want to have the ability to select elements that are influenced by this load. Here I can use the action button, update to the members selections, and I can quickly select these members from the cylindrical shell. Here, for this, I can also update the selection by using, let's say, only these sections. And now if I go for generation of load, I can generate them by using this action button, I can see that the dead load was generated as I would expect. So everything is acting in radial radial direction, and it's also linearly increasing throughout the height of the model. For the dead load, this I have already implemented. The imposed load is, I think, very simple. Let's play 0.75 kilonewtons per square meters, and place them just on the surfaces of the roof. That's only a load case to add. And let's continue with the wind load, as this is the most interesting one of loading of the tanks. So I will model. I have prepared a table in Excel in order to calculate the action of the wind pressure along the surface of the tank. For this shape and this height of the tank, I have it calculated elsewhere, the coefficient of the basic pressure, and here I have the CPE parameters based on the angle deviating from the angle of wind action. So I have here by 10 degrees specified values of exposure coefficients. So what I want to do here in terms of wind, I want to act in pretty similar way, or input it in very similar way as the filling, but making multiple, or in this task, 36 strips of different loading patterns or loading values. What I can do here is I will set the snapping points to 9, because one of my segment is 45 degrees, so one nth of it would be 5 degrees, and I want it to stretch through two separate shells. So this is the granularity that I am going to choose, and again I can start inputting the free load. So here I can see the nose that I'm selecting, and here at the 0 plane I can see the actual shape of the loading pattern. So I will model I'm going to model it right like this, even all the way to the bottom, and back here, and at the top I already have 2 points. So I generated strip of load as you can see here. What I will do now is very similar trick as I did before. I apply only midpoints, and I move this load to the edge where I placed it. First thing what I will have to do is I have to define the acting members and also the validity, because I don't want this load to act on both front and back. I want it to act only on the front in this case. So I'm going to first set validity from 2, and I want the validity from, let's say, -3 meters, which is very close to the axis of the silo, and let's say to plus 0.5 meters. I want to select members that I'm going to apply wind load on, and now I can again select those members. I can now hit generate loads in order to see that everything has gone as expected, and here I can see that it hasn't, because I apparently set it the other way around. Let me here go to the loads, and instead of generated, have a look at original, plus generated, and I can see that in this case the inner part is second one. If I again hit generate, I will get strips of load generated along the uh, height of the structure. Here I will also place that I want to have distribution in linear manner and not constant on the height. And also what I again can do is use the multiple copy feature in order to copy this load 36 times by 10 degree. And now I have copied everything around the structure. What I will do now is I will use the table input feature in the SCIA Engineer, where I can modify all these inputted loads at the same time with the use of my Excel. So what I will do here is I'm going to select my structure. I'm going to hit select or filter only by selected members. I'm going for loads, and I want to see free surface loads. And these are the loads that I inputted on my silo in the load case wind load. Because I made all of those basically one after another, because it was multi-copied, so it goes around the copying manner. I know that all the impulses are sorted by the angle. So now I can go into my helping Excel, and here I have exactly the same thing. I can just copy these two columns with the first or the value at the bottom and value at the top. I can go here and I can place those calculated numbers right in the table input. And now you can see, if I magnify it a little, that I have achieved the loading pattern as I have in the figure here in the Excel, and exactly as the Eurocode asks me to define such loads. So however, I can see I inputted it, or the values are other way around, because yeah, the bigger value should be of course on the top. This can happen, of course. I can fix it very quickly just by switching the columns, or inputting this one here, and the other one to the first column. And now I have it as I would like it to. Now if I generated the loads, the separate strips of loads will get generated in the exactly same way as before for the single strip. So what I can do now is I can proceed to analysis, because the structure is now done. I have all the loading in place, and I have here some predefined combinations that I'm okay with having just those. So I can now run the analysis. So first thing here that I'm going to talk about is the mesh size. The default mesh size is in new project 1 meter, which is quite unuseful for structures of this size and this type. Here I would say that I would use let's say mesh size about 10 centimeters to get the most accurate results. Currently I have here 250, because of course I want you to see the results quickly in this webinar, but in real life project I would use much finer mesh, or mesh refinement, and I will show and talk a bit about that in a second. So this project should be calculated very simply, and of course I have prepared already calculated project, but this one shall take only a few minutes to calculate. If I go in the meantime, or let's wait like 20 seconds. If I imposed the inputted the wind load, the shape of the deformed structure that I would assume will be the case is similar to this one. Of course, the shape is available both on 2D or 3D displacement, and you see that the calculation is taking longer than I would see fit, but let's hold with it together. The one tip that I can tell you in advance about showing the results of 3D deformation in this case is that 3D displacement shows deformed structures in terms of volumes in the standard setting. You can see that both volumes of the 1D members and 2D members are respected and drawn, and this gives you very realistic touch or realistic behavior of the structure. We have, however, also a simplified form that is called wireframe mode of calculating or displaying results, and I'm going to show you how much faster this one is and how relevant it is while looking at the results in structure like this one. Okay, I can see that it takes some time, so I will start speaking about checks of the rotational shells. First thing that I would like to introduce you with is the SCIA Garage project. This is project made by enthusiasts in SCIA team that they are creating mostly in their free time to help you, our customers, by tweaks and little tools that you are able to use in your everyday designs, but these are not incorporated in the setup of SCIA Engineer. You can find it in the resource center at SCIA resources.scia.net under Garage section. And if you scroll here all the way down, I added here the shell buckling check that I'm going to show you in a few moments. This check is free for you to download and input in your SCIA Engineer for further use. Now I can see that my calculation is finished, so I can view the results. Let me go to 3D displacement and show you the 3D displaced structure for the wind. Now if I hit F5 refresh, you can see that evaluating these results take approximately 10 seconds, and I have the deformed structure like that. However, if I use the wireframe option here and I hit refresh, you can see that I see the results basically instantaneously, because beams are now represented by only single lines, and the shells or 2D members are just by their member, or by their single structural plane. So it's very fast. It's like 10 or 20 times faster than the full 3D displacement. If I here look at the stability analysis that I had calculated as well, I can view, for example, the first mode, and I can see here what is happening with the results. And I can see that, as I would expect, the local buckling is occurring in the vicinity of the supporting column. And to show you more, I will now switch to a different project, and I will talk more about the refinement or the mesh refinement in order to get more precise results. So here in this project, that is a bit, you can see it's a bit optimized, because for this local buckling behavior, I added specific stiffeners, and here also plate stiffener for the contact with the column. Here, if I look at this specific buckling shape, which you can see is with factor 30, you can see that the buckling of the shell is by stiffening this plate by first having bigger thickness of it, and using the stiffeners, I can see that I have much bigger stability factor than before for such shape. What I can also see is that to actually evaluate and to see the shape here, my web or my FEM mesh is very coarse, and coarse mesh in this matter means inaccurate results, and it's showing that the results are implying that the shell is behaving much more stiff than it really does with the finer mesh. So here it is very important to use mesh that is uh, refined in the areas that are interesting for us. So let me first in the view parameters set to display mesh, and because the mesh setting that I showed even before is about 25 centimeters mesh size, seems that these stiffening rings is divided only in 4 mesh elements by its height. I can go to calculation and mesh and choose the local mesh refinement feature that will allow me to use finer mesh, let's say 4 centimeters mesh size, for only selected parts of the structure. Let me apply these on all these members that I have here, and also I am interested in the area above the column in this part. So for this, I can use the nodal mesh refinement. I can here set radius of such mesh refinement, and I can click on separate nodes of the shell above column, and you can see that you will get such shape of the mesh refinement, which is completely covering the view. So let me generate mesh here, and then hide the mesh refinement volumes. Okay, so it's taking a few seconds to finish. Now I have finished the mesh calculation. Let me not draw the refinement, and you can see what actually I did. I have very fine mesh in the stiffening ring where I want more detailed analysis. I also have finer mesh in the area beneath the nodal refinement, and you can see that I inputted 2, so on the other side of the silo these are not inputted. This model, however, takes more time to calculate, so I can show you here a model that I have that has the exact same, very similar settings applied to it, and I can go to results, and I will hide the mesh again here to get a clearer view. And if I go to 3D displacement, I can see that my buckling factors get much smaller than I had before, and that is that I have much more precise analysis in the areas that are interesting. You can see that now the shape is very clear, its shape is visible, and this implies that even the results that we have for the stability factor are more precise than what we had before. So we can see that we have these in this model. We have the local buckling as our eighth shape. Let's have a look at the first shapes, how the silo is behaving in a global manner, and we can see that the buckling of the shell itself and not the stiffening ring is first occurring in the shell of the silo right above the column. This behavior is, I believe, expected for this structure, and we can have a closer look at checks of this silo with respect of the stability factor. For that, I will use the integrated design forms that we have in SCIA Engineer, and I already have the download from the SCIA Garage, the check available in my SCIA Engineer. So what I'm going to do first is I'm going to add member data, and here I have to add the critical factor. I don't remember it entirely, but I think it was something like 13.5. The manufacturing quality and the shell radius. Shell radius in my case is 3150 millimeters, and I can put these values on shells that I have here. Let's put it quickly on all of them, and now I am able to see which shells actually have it. Let's go now for the check, and here the check will work with let's say in this time I wrote social classes. It takes few seconds to complete, so I will make some current selection of members. Let's say I'm going to select these two shell members, and I want to see this value, which is the utilization of the shell or membrane element. Even though the mesh is refined, the check don't take much time, and now we can see where we have the critical parts. Critical parts that are not okay are right above the column, which seems logical, because first, the buckling factor is not as high as we would like. This structure would require some further stiffening, either by, I can very quickly put these or modify these stiffeners to get a bit up, or I can, what I would most likely do is I would increase the shell thickness in this area in order to have higher buckling factor for the first shape of the critical load. So this would reduce also of course my check value in this area. This check is also provided with detailed output, which you can see while using the preview. Here you can see which values of stresses are acting, what is the strength, and also the utilization in some areas. So I now covered even the checks. Let's go and have a brief look at the engineering report and its capabilities. For that, I will get back to this model with results, but without the refined mesh, because there the results require much less time to get calculated, and I will need results in my engineering report as well. So My model is now opened. I can see that I have results available, and I can go to Engineering Report. In Engineering Report, I have nothing but a blank new Engineering Report with no items whatsoever. What I will show you now, and I recommend you to watch or follow us also on YouTube, because here we add our recordings from our webinars, and also the recording from today's webinar will be also available. I very recommend for the topics that I'm going to cover now to have a look at the webinar section, and let's have a look at the Create Project Documentation in SCIA Engineer. It's a webinar that is linked to something that I'm be showing right now. And now I will let's say that I created very similar structure for different project, and I saved the whole engineering report as a template. Just by double clicking on it here in the report templates under user templates, I can have it loaded and have the entire documentation that I created for other project in this very engineering report, and it will get refreshed based on what is actually in this engineering report and not in the previous one. You can here see that it takes like multiple, or let's say it takes a minute to refresh, because besides what you might think here, there is quite a lot of items. It's not a big engineering report. It's prepared for this webinar, so it takes very quite reasonable time to get refreshed. Now it's evaluating results from the that were called from the pictures in the engineering report. You can see the progress bar is running here in the background, and when all progress bars are up, then I will have my engineering report generated. Shouldn't take now more than 20 seconds. And here in this engineering report, I have all stuff in it that I'm going to show you, but not talk much into detail about them. For that, I really recommend the webinar that I recorded previously about specifically about these capabilities of the engineering report. So now we are almost there. See that this is the last progress bar running in the SCIA Engineer, and now I have everything refreshed. You can see here that some pictures that are here became unrefreshed, and you can see entirely different structure that was that served as preparation for this template. Just by regenerate outdated, I can regenerate these pictures, and if I have my structure created in very similar way, I use layers, I use load cases, stuff like that consistently in my projects, then I can use these templates very efficiently. So first capability that I have here, you can see I have the cover page that is basically external reference. Of course, it's different for any project, but the reference can be very quickly adapted, and so that's the cover letter. You can see here I can add customized header and footer. I have table of content, some text fields that are describing. Basically what I'm doing here in simplified form is making the whole structural document I need entirely in the engineering report without the necessity of using Excel. You can see that I can also link external Excel file for, let's say in this case, calculating loading for dead loads on my structure. And of course, I can add the libraries from the SCIA Engineer, such as profiles and much more. I can see that the pictures got regenerated, and I can see my structure available here instead of the model that was there before. I can see it from two different looks, and also here I can see how I use in this the indented files. You can indent, let's say, results or images under some tables. Let's say in this case I use layers, load cases, or combinations, and they will show only the part that is available within that specific layer, or that it will show load that is only in the specific load case. So in this layer I have only the tank, so I can see it. In the second picture I have only the supporting members, and by inputting only one image and also inputting it through the template, I can see both images are here. For the load cases it works the same. Here I have the self weight. Okay, there is nothing drawn here, but here for the filling I can see the load being generated by the filling, also by the other dead load, by the imposed load on roof, and also by the wind. What I can also do, I can indent result images under, let's say, in this time combinations. So combinations are, I have 3 combinations in this project, and I can see that the deformed structure is displayed for the first one. This is the ULS with filled tank. Then I can have the deformed structure for the SLS with empty tank. You can see here the wind is of course the dominant force, and also I can have another combination. These principles apply quite generally, so you can indent any type of either result images or result tables under combinations or layers or load cases in order to get filtered uh, filtered results or filtered tables based on what's actually in there. I can show one more application here. Let's here add uh, the load impulses, because here I have, for example, free surface loads and surface loads I have available in my project. If I double click on both, I get them also under the load case. If I now hit regenerate this chapter, I will see both image of the load case that I had previously in it, but I will also see uh, filtered tables. You can see that for the first load effect there is nothing, because the self-weight doesn't contain any surface load nor free surface load. But here for the fill, I can see that I get also the table of the surface loads that are being generated or that are being inputted in the load case. And for the load case 3, which is the dead load, I can also see list of the surface loads only for this very load case. So in this way you can create very structured engineering reports that are basically providing all-in-one solutions. So even with customizable headers, footers, and cover page, you can create your whole structure document for this type of structure and then reuse it again and again with ease and efficiency. So this is all that I wanted to share with you in this webinar. I'm thankful for your attendance and your questions or remarks, and I also thank you in advance if you consider using our SCIA Garage content or looking up our webinars on YouTube. Thank you very much, and bye bye.